3I Atlas, a mysterious interstellar visitor billions of years old, finally making its closest approach to Earth. Whether it's an ancient comet or an alien spacecraft, one thing is certain: this interstellar flyby has sparked wonder about the universe.
Here's a question that sounds completely backwards. Why would scientists get more excited about an interstellar visitor as it leaves our solar system than when it arrived? Think about it. You've got this ancient cosmic wanderer, 3I Atlas, screaming through our neighbourhood at 68 kilometres per second, the fastest object humanity has ever tracked. It's carrying chemical secrets from another star system, information that our sun has never touched, from a place our telescopes could never see. And the moment it starts heading away from us, that's when every major observatory on Earth suddenly gets very, very interested. Yeah, that does seem backwards. But here's the thing. And we promise this will make sense in about 30 seconds. The departure phase of an interstellar comet isn't the end of the show. It's actually the main event. Everything before that, just the opening act. The heat that takes its time. So let us give you the answer right now, because you didn't click on this to wait around. Thermal lag. When 3I Atlas approached the sun, its surface started heating up. Solar radiation began penetrating the outer layers, kickstarting a transformation. But here's what nobody tells you about objects that have spent billions of years in the absolute cold of interstellar space. Heat doesn't just instantly reach the center. The warmth needs time. Time to sink deeper. Time to wake up volatiles that have been sleeping since before Earth existed. Think of it like taking a frozen turkey out of the freezer. The outside thaws pretty quickly, but the inside stays frozen for hours. Now imagine that turkey has been frozen for 14 billion years, and instead of sitting in your kitchen, it's hurtling through space at 68 kilometers per second. The temperature difference between the surface and the core is genuinely staggering, and heat conduction through ice is a slow process. During the approach, we saw what the sun could do to the surface. But the departure, that's when the heat finally reaches the interior. That's when the comet starts releasing gases and materials that were locked away far beneath the irradiated crust, materials that have been in cold storage since before our solar system even formed. The departure becomes a delayed confession, a revelation of hidden chemistry, secrets that the approach could only hint at. And oh, would you look at that? Suddenly, the paradox makes sense. An object becomes more valuable precisely when it starts moving away from us. Not poetry, physics. This is why, as 3I Atlas passed Earth at nearly twice our distance from the Sun and began its outbound journey, every major telescope on the planet, and quite a few in orbit, trained their instruments not to say goodbye, but to witness what the comet would finally reveal. And what it revealed? Well, let's just say it challenged everything astronomers thought they knew about comets, about interstellar chemistry, and about the very fabric of space between stars. The impossible chemistry. Let's back up for a second and tell you how we even found this thing, because the discovery story is genuinely wild. The Atlas telescope in Chile caught something unusual in some survey images, a faint smudge moving against the background stars. Within hours, archival searches revealed the object had been lurking in older images, basically hiding in plain sight. And within a day, observatories around the world had contributed enough observations to deliver the verdict. This was no ordinary comet. Its orbital eccentricity, basically how extreme its path is, came in at 6.139. To put that in perspective, the first interstellar object, Oumuamua, had an eccentricity of just 1.2. The second, Borisov, measured 3.4. But 3I Atlas, its trajectory was so extreme that no force within our solar system could possibly have created it. This object came from somewhere else entirely, from the depths of interstellar space, where it had been drifting for longer than Earth has existed. What made the discovery even more remarkable was how the comet had approached. It passed directly in front of the galactic center, its faint light obscured by the dense star fields of Sagittarius. An amateur astronomer pointed out that this cosmic coincidence nearly caused us to miss it entirely. A slightly different trajectory, and we might have spotted it weeks earlier, or not at all. The universe was basically playing hide and seek, and we almost lost. Now, unlike Oumuamua, which showed no cometary activity and sparked all kinds of wild speculation about artificial origins, this visitor was unmistakably a comet. It had a fuzzy appearance, a developing coma, and all the telltale signs of volatile ices sublimating into space. No alien spacecraft theories required. This was just an honest-to-goodness ball of ancient ice and rock, doing exactly what comets do. But here's where things get weird. Pre-discovery images traced the comet back to when it was already active at more than 6 astronomical units from the Sun. And that's a problem, because water ice doesn't start sublimating until around 3 AU. For this comet to be active at twice that distance meant it contained something far more volatile than water. Something was boiling off this thing way out in the cold reaches of our solar system, long before it should have woken up. This is the kind of mystery that makes astronomers lose sleep. Something was fundamentally different about this comet's composition, and the only way to figure out what was to point our best instruments at it and hope the light would tell us something useful. When James Webb Space Telescope trained its infrared eyes on 3I Atlas, the data that came back genuinely defied expectations. Carbon dioxide dominated everything. The comet was releasing roughly 20 times more carbon dioxide than water, which is basically backwards from every comet we've ever observed in our solar system. Statistically speaking, this wasn't a minor anomaly. It was a screaming outlier. Let's put this another way. Imagine you've spent your entire career studying dogs, and then one day a creature walks in that looks like a dog, moves like a dog, barks like a dog, but has the internal biology of a dolphin. That's the level of, wait, what? We're dealing with here. The implications hit hard. Carbon dioxide condenses at much lower temperatures than water, which means 3I Atlas must have formed far from its parent star, in the cold outer reaches of some distant planetary system. This comet was born in darkness, in a region so cold that carbon dioxide could freeze into solid ice, waiting billions of years to be heated for the first time by our Sun. But wait, it gets stranger. Ground-based telescopes detected atomic nickel being released from the comet. In our solar system, nickel and iron typically show up together, released from the same mineral structures. But 3I Atlas showed nickel without the expected iron signature. Nobody had a good explanation for that. It was as if the comet was following different rules of chemistry, which, in a sense, it was. Even stranger was what the comet didn't contain. Despite being clearly active with a bright coma, 3I Atlas proved remarkably depleted in carbon chain molecules, the compounds that give many comets their characteristic green color during approach. Scientists classified it among the most carbon-depleted comets ever observed. So you've got a comet that's releasing way too much carbon dioxide, has nickel but no iron, and is missing the carbon compounds that should be there. What's going on? A landmark hypothesis emerged. Researchers proposed that 3I Atlas had spent so long in interstellar space, perhaps 7 to 14 billion years, that galactic cosmic rays had fundamentally transformed its outer layers. This radiation converted carbon monoxide into carbon dioxide, creating an organic-rich crust in the outer 15 to 20 meters of the nucleus. What we were observing wasn't the comet's original composition. It was what billions of years of cosmic bombardment had made of it. The universe had essentially rewritten this comet's chemistry while it drifted between the stars, leaving us with a palimpsest of cosmic history. Okay then, that was always allowed, we guess. This is where the departure phase really starts to pay dividends, the comet that changed colors. As 3I Atlas swung around the Sun and began heading back out, astronomers noticed something remarkable. The comet was changing colors. During approach, it showed one spectral signature. During departure, a different one entirely. The outbound comet was showing us chemistry that the inbound comet physically could not reveal. Remember that thermal lag we talked about? Here it is in action. The heat had finally penetrated deep enough to release gases from pristine interior ice, material that had been shielded from cosmic radiation for billions of years. Scientists cautioned that this might not represent a true surface color change, but rather different gas species dominating at different phases of the journey. Either way, the message was clear. We were seeing the comet's secret identity. The approach showed us the cosmic radiation-altered exterior. The departure revealed what was actually underneath, the original chemistry from whatever alien solar system had ejected this visitor billions of years ago. But the color change wasn't even the most dramatic part. Observations from a Spanish observatory revealed evidence of cryovolcanic eruptions, actual ice volcanoes. Spiral jets of gas and dust were emanating from the nucleus, with a sharp and lasting surge in brightness. Unlike typical sublimation, where ices simply evaporate from the surface, this appeared to represent sustained volcanic activity across the water-ice surface. The explanation was elegant. Solar system comets develop protective dust mantles over billions of years of close solar encounters, insulating their interiors. But 3I Atlas had never passed close to any star before. Its surface was essentially pristine, no accumulated protective layer. When solar heat reached the ice, there was nothing to stop the violent response. Ice volcanoes erupted across the surface, releasing material from depths that local comets keep forever sealed. We were watching a comet throw a tantrum because it had never experienced warmth before. Like a creature from the deep ocean suddenly exposed to sunlight for the first time in its existence. Throughout the passage, the coma grew from about 13,000 kilometers in diameter at discovery to over 26,000 kilometers at maximum extent. That's roughly twice the diameter of Earth, by the way, a cloud of gas and dust larger than our entire planet, streaming off an object maybe a few kilometers wide. The dust grains proved unusually large, several micrometers compared to the submicron particles typical of local comets. And then there was the anti-tail, a feature pointing directly toward the sun that defied conventional understanding and suggested this visitor was carrying physics we had never encountered before. Most comet tails point away from the sun, pushed by solar wind and radiation pressure. But 3I Atlas was doing something different, and nobody could fully explain why. Let's be clear about what we're witnessing here. An object older than our solar system, carrying chemical signatures from an environment entirely unlike our own, putting on a show that intensified the further away it got. Every day it receded gave us more data, not less. Why this changes everything. Now, 3I Atlas posed no threat to Earth. At nearly twice our distance from the Sun, it was never coming anywhere close, but its arrival triggered something unprecedented. The first inclusion of an interstellar object in the International Asteroid Warning Network, a UN-backed coordination body dedicated to protecting Earth from cosmic impacts. Why would they bother with something that wasn't dangerous? Because the next one might be. The Planetary defense exercise wasn't about responding to 3I Atlas specifically. It was about establishing protocols for future visitors that might not arrive on such benign trajectories. Interstellar objects create unique challenges that local asteroids and comets simply don't. Think about it. Unknown origin systems with unknown compositions make chemical behavior unpredictable. Outgassing can alter trajectories in ways pure gravity calculations can't anticipate. Extreme velocities mean limited observation windows and potentially very little warning. And compositions altered by cosmic radiation over billions of years create complete unknowns in material behavior. How do you deflect something when you don't even know what it's made of? When the physics of its surface have been transformed by processes we've never witnessed up close? These aren't theoretical concerns. They're the practical nightmares that planetary defense scientists now have to take seriously. Here's the really sobering part. 3I Atlas approached from a direction near the Sun, making it invisible during part of its journey. Objects coming from the sunward direction could arrive with minimal warning. This is a fundamental vulnerability in our detection capabilities, and it's one that space agencies are now scrambling to address with new missions designed to watch the blind spots. The departure of 3I Atlas also provided something invaluable: tracking data that extended our ability to predict future interstellar trajectories. Long baseline observations, spread over months as the comet receded, refined orbital calculations to unprecedented precision. Every day the comet remained observable was another data point for understanding how these visitors move through our cosmic neighbourhood. The longer we watched, the better we got at predicting where interstellar objects might come from next, and more importantly, where they might be going. And speaking of the future, here's where things get genuinely exciting. The chase we might actually pull off. Direct interception of 3I Atlas within the inner solar system? Impossible. It's moving too fast, its trajectory already carrying it beyond practical reach. But the story doesn't end there. In fact, for mission planners and space dreamers alike, this is where it gets interesting. Researchers have analysed what it would take to actually catch this thing. A spacecraft launching in 2035 could potentially intercept the comet using something called solar obverth maneuvers, gravitational slingshots that use close solar passes to dramatically increase velocity. It's ambitious, but it's not science fiction. The math works, the technology exists. We just need the will and the funding. Realistically, ESA's Comet Interceptor mission, launching in 2029, represents the best near-term opportunity for studying interstellar visitors. This 3 spacecraft configuration will wait at a gravitationally stable point in space for up to 3 years, ready to sprint toward a suitable target on short notice. The science team has stated clearly, if an interstellar object appears, they will not let that opportunity pass. It's like having a fire truck parked at the station, engine running, just waiting for the alarm. A major research institute completed a mission study finding 3I Atlas's trajectory within the interceptable range of their design. The key revelation: interstellar object flyby reconnaissance is both feasible and affordable. We're not talking about moonshot budgets here. We're talking about the kind of missions space agencies already know how to do. Perhaps most profound is what 3I Atlas tells us about cosmic history. Various studies place its age between 3 and 14 billion years. Think about that for a second. This comet might be older than our solar system itself, a time capsule from the early galaxy when different stellar conditions prevailed, when the universe was still figuring out how to make stars and planets. Its potential thick disk origin suggests formation around a low metallicity star, one with heavy element abundance far lower than our Sun. Every observation adds to a portrait of cosmic chemistry spanning billions of years and countless light years. We're not just studying a comet, we're reading a message from an era of the universe that no longer exists, written in ice and rock and the subtle signatures of ancient chemistry. What it left behind. As 3I Atlas departs, crossing Jupiter's orbit soon, Saturn's after that, and reaching Pluto's distance by 2029, it leaves behind a treasure of data that will take years to fully analyze. Major space telescopes scheduled specific observation windows just to characterize the compositional changes during departure. Others committed to monitoring the comet's recession through early 2026. Ground-based observatories announced they would continue tracking 3I Atlas as it left the solar system, detecting changes in gas composition and outburst behavior all the way out. The passage near Jupiter offered one final major observation opportunity before the comet faded beyond the reach of even our most powerful instruments. But here's the thing that really matters. and we want to make sure you walk away understanding this. We used to think interstellar visitors were rare. Oumuamua showed up in 2017, and everyone thought it was a once-in-a-lifetime event. Then Borisov appeared in 2019. Now 3I Atlas in 2025. Scientists now estimate roughly 60 interstellar objects pass within Jupiter's orbit at any given time. 60. Let that sink in for a moment. At any given time, there are roughly 60 pieces of other star systems drifting through the same region of space where we live, where we've built our civilization, where we launched our first rockets and satellites. They've always been there. We just couldn't see them. We're not dealing with cosmic rarities. We're dealing with a cosmic rush hour that we only recently developed the technology to notice. The Vera C. Rubin Observatory, now operational in Chile, will dramatically improve early detection of future visitors. We're going to find more of these things, a lot more. And each discovery will refine our understanding of what's normal for interstellar objects and what's genuinely strange. And each one that passes through will tell us something new about how other planetary systems form, about what happens to material drifting between stars for billions of years, about the chemical diversity of our galaxy. We've gone from interstellar objects might exist to they're everywhere, and we're finally learning to see them. 3I Atlas demonstrated that interstellar visitors are neither rare nor unknowable. They are physical pieces of other star systems, cosmic messengers carrying chemical signatures from environments entirely unlike our own. They've been passing through our neighbourhood for billions of years. We just weren't looking. And humanity is finally developing the tools to read their messages. So next time someone tells you the best part of a journey is the arrival, you can tell them about the interstellar comet that proved otherwise. Sometimes the most valuable part of the show is the exit, when an ancient traveller finally reveals what it's been hiding for longer than our world has existed. What are your thoughts on 3I Atlas's journey? Share them in the comments.